Today, we're going to do some work. What's work? What's that? So you get up and go to bed in the same spot every day so you don't do any work?
My physics teacher told me that work is doing something and ending up with things about afterwards or something like that. Since we get up in the same spot, we want to go to bed in the same spot and want to take the teacher to start doing work. The physics definition of work.
Okay. All right, so work is, for us, for example, let's say I were to take this book and I were to lift this book straight up. That would be work. How much work? How do you figure out work? Work is force times distance.
What if you drop it on the ground, then what's doing the work?
Then the force is gravity. Now, I'm not doing any work in that case. Gravity's doing some stuff. Sure. The book goes crash. Goes boom. Book goes boom. Okay, well that's pretty easy when I'm lifting a book. As I lift this book, does the force change? Does it change? Does the weight of this book, is it any different here than it was there? No? The force is exactly the same? The distance is changing. So in this case, the weight of the book is constant, so the force is constant, correct? And I lift it up. So how heavy is this book? You think your calculus book only weighs 1 pound? Okay, so let's call it 1 pound. And how high am I lifting it? 1 foot? So how much work am I doing? Well, how much does it weigh? So it must be 1 pound of force to lift it. No, work is completely irrelevant of how fast you go. If I lift it real slow like this, or if I lift it real fast, I've done the same amount of work if I've moved it the same distance. Work is irrelevant of the speed. So, we're saying this book weighs 1 pound. So the work to lift that book would be 1 pound times 1 foot. So we would do 1, what's the unit on work? Joule if you're working in the metric system, but I'm clearly not working in the metric system. Foot-pounds. So I would do 1 foot-pound of work. The unit for work is joules if you're working in the metric system. That's correct.
Is that really a thing, foot-pound?
I wrote it, didn't I? Foot-pound. It must be a real thing. Yes, the units of work in the English system are called foot-pounds. Because it's feet times weight. So it's feet times pound. We call them foot-pounds. In metric, it's Newton meters, which are generally known as joules.
I just think that name is the most bizarre thing I've ever heard.
Foot-pound?
Yeah.
Foot-pound. Yeah. It's a common unit of work. You hear it if you use a torque wrench, you'll hear foot-pounds.
Or car.
For a car, torque wrench, yep. All right. Well, that's very easy to do since the weight of the book doesn't change. Are there situations where objects are moving? That should be a related rate problem. How fast is the soda spreading on the floor?
Well,
it's the wrong section.
Is there somewhere you guys can ask for something? That's where I'm going.
Yeah. All right. Anyway, lifting the book, computing the work done and lifting the book is very, very easy because the weight of the book does not change. Is it possible to have variable force at times where things do change? Yes. Can you give me some examples?
You were lifting a bucket that was filling up with water at the same time.
If I was lifting a bucket that was filling up with water at the same time, the bucket would be getting heavier. Or if I was lifting up a bucket that was leaking, the bucket would be getting lighter. So that would be an example of, as I lift, my force would change. It's a good example.
Lifting something in and out of water.
Yes, that's true, but that would be a very discontinuous function because it would have one weight within the water, and as soon as you popped out of the water, it would have a different weight. So that is change in force, that's true, but it would be a discontinuous function. And we don't like that. How come we don't like discontinuous functions? It's difficult to take antiderivatives of them. Yes.
What about
A rocket like going up in the atmosphere because you're like zero gravity once you get out of the atmosphere. Well, less gravity, zero gravity, and then when you're the rocket, the weight when it's taking off still has a 9.81 meters per second squared.
Okay, so if I were to take my book and put it in a rocket ship and blast the rocket ship into space, the weight of the book actually would change. The reality is, when I lift this book 1 foot, the weight really does change.
Yeah.
Because weight is related to the distance from the center of the Earth. That's the force due to gravity. The thing is, it doesn't change enough to be measurable, really. But it actually does change. But if I shoot it into space, if I shoot it several thousand miles into the air, then the weight of the book does change significantly, and the amount of work as it goes up would, the amount of force required as it goes up would change. Okay? So that's a good example. And we'll do some examples of that, of what happens when you shoot a rocket into space, what happens to the force required to lift the rocket and lift the payload, and so on and so forth.
It gets less under the
It gets less as the rocket gets higher. That's correct. Other examples where the force changes.
Wouldn't that be just like a climber on Everest? There's less air up in that, like less dense air, so it's hard to breathe.
That's true. The higher up you get, the less oxygen there is. It does get harder to breathe. That's an interesting question. Does your weight change significantly when you get to the top of Mount Everest? Would your weight be a couple pounds lower because you're a couple thousand feet higher up? I don't know. We could figure it out. I don't know how tall Mount Everest is off the top of my head, though.
Pushing something up a slope.
Pushing something up a slope, that would be fairly constant as long as the slope...
Well, I mean, like, because it'll become less, like, is it gradual, or... Like,
If it was not a straight line
yes.
slope, then absolutely, as it got steeper,
It would get
more force would be required. If it shallowed out, less force would be required to push it up the hill. That's true.
If you were to pick the book up faster, what would the normal force increase?
I don't think so. I'm not sure. Another classic example of where force changes is if you have a spring. What happens as you squeeze a spring? The more you squeeze it, the harder it gets to squeeze. Or if you stretch it, same idea. And that's somebody's famous law. Whose law is that? Whose famous law is it about springs? Anybody know? Nope. Hooke's law. Hooke's law of springs. Okay, so let's think about this. We need to come up with what's going to happen when force changes, when force is not a constant. So we have some object here. Let's say we have a spring.
It sounds like you've gotten into physics.
Oh, this is physics. This is completely physics. So we have a spring. And as we squeeze this spring together, so this side is going to be fixed, this side is not moving. And we're going to squeeze it, so we're going to push that side that way. As we squeeze it, the force required to squeeze it increases. So the force is going to get stronger and stronger and stronger, amount of force needed. So how are we going to, if we want to squeeze it from here to there, for example, if we want to squish it that much, how are we going to figure out the work done? We would certainly need to know the distance. And?
The amount of force pushing on the spring and how much they're pushing back.
Okay. But that amount of force would change, wouldn't it? When I'm right here, the force is going to be one amount. When I move over a little bit, the force is going to be more. When I move over a little bit more, the force is going to be more yet. So on and so forth. We're going to integrate. Why are we going to integrate? What we're going to consider is taking this spring and squeezing it little by little at a time. And at each spot, we could figure out the force, couldn't we?
So is it infinitely adding up the amount of forces?
So we're going to infinitely add the amount of forces. That's correct. So we're going to have our work is going to be the integral of our force function. We'll have to have some sort of function for force times distance. How far is my spring squishing each time I move it? A tiny little bit, and that tiny little bit we call dx. So there's going to be our method for figuring out work when the force is variable. Yes?
Doesn't it the same apply for like when a bullet you put an object on the bullet that how much force and distance when it hits the stop or the
So if we were to shoot off a gun and the bullet were to hit the wall, how far it would penetrate into the wall would depend on how fast the bullet's going.
how far away it was.
How what?
How far away it was. If you shoot it from back here, it's going to go less than if you shoot it from 2 feet away from the wall.
Right, but that's because it changes the speed. Because the bullet, if you shoot from further away, the bullet has slowed down by the time it gets to the wall. That distance really doesn't matter. What matters is how fast is the bullet going when it hits the wall. So the distance you shoot from changes the speed, but it's really the speed that matters. The density of the object, the composite density of the bullet itself.
Composition of the wall.
Composition of the wall, which would be the same as the density of the wall, correct? But there would be work involved because that bullet, its momentum would have a force going behind it. And when it hits the wall, of course, the momentum and things change, and that's why you get a big hole in your wall. We won't be shooting any bullets. All right, I'm just going to grab a problem out of the book here. Let's see. Number 7. Number 7 says a force of 20 pounds stretches a spring 9 inches in an exercise machine. Find the work done in stretching the spring 1 foot from its natural position. All right, the first thing you need to know in order to answer this question is you need to know Hooke's law. Anybody know Hooke's law? Nope. It does have a K and an X in it. It's a much simpler formula than that. Hooke's law says the force is some constant times the distance.
How do you spell the guy's name? Oh, that one. Okay.
Hooke's law. All right, so in this case, we are told that a force of 20 pounds stretches a spring 9 inches. So force would be 20 pounds, stretches the spring 9 inches. So that gives us our value for K. K is 20 over 9. So our force function, f of x, is 20 over 9x. All right, now it wants to know. Find the work done in stretching the spring 1 foot from its natural position. So we're going to have work is the integral of force times distance. So that's going to be the integral. What's our force function? 20 over 9 x dx. And I need to know my interval. 0 to 12. Very good. Why 0 to 12?
Because you're working in inches. So you have to go from 0 inches to 12.
Very good.
Goes its neutral position.
What's that? Why not 9 to 12? Okay. Another good question. First off, it has to be, we agreed that it has to be 12 because this 9 was in inches. My other option would have been to write 9 in terms of feet, and then I could have used a 1 right there. But I think it's easier to use 12 though. All right, so why is it 0 to 12 and not 9 to 12? Correct. So notice it said, find the work done in stretching the spring 1 foot from its natural position. So it might have asked, find the work in stretching the spring from 9 inches to 1 foot, and then your integral would have gone 9 to 12. But in this case, it said from natural position. Natural position is always 0. All right, well, that's a pretty easy antiderivative. We find the antiderivative. What's the antiderivative of 20 over 9x? Thought it was an easy one anyway.
20 over 9x squared
20 over 9x squared over
over 2.
2. I'm going to write that as 10 over 9 x squared, because 20 divided by 2 is 10. Evaluate from 0 to 12. So that would be 10 over 9 times 144. So that's 1440 over 9. And my units would be inch pounds. You thought foot pounds sounded funny. How do you like inch pounds?
Worse.
It's worse. All right. Inch pounds. Not a standard unit of work. If this were a physics class, you would probably be required to convert that to foot pounds. And how would you convert it to foot pounds? Multiply by 12 or divide by 12? So if you have 12 inches, you're going to multiply by 12 and tell me it's 144 feet?
Yeah.
Yeah? Okay, you can tell me that. I won't believe it. You would divide by 12. You would divide by 12 to convert to foot pounds.
12 over 1, I just mixed them up.
12 over 1, 1 over 12. All right, how about we skip to number 11. Neglecting air resistance and weight of the propellant, determine the work done in propelling a 5-ton satellite to a height of 100 miles above the Earth and B, 300 miles above the Earth. All right, so you need to know a few things about gravity. First off, if this is the Earth, and this is something sitting on the surface of the Earth, what can you tell me about gravity?
Pulls towards the center.
Gravity is always pulling towards the center of the Earth. So gravity is pulling the object this way. What's the radius of the Earth? How many miles?
15,000
That's like the size of Jupiter, not Earth. The radius of the Earth is about 4,000 miles. Oh, he might have meant the circumference?
Yeah.
Maybe.
Then I put like 32,000 miles.
I just wanted the radius. All right. So, what else do you know about gravity?
9.81 meters per second squared.
Okay, that's the force due to gravity.
Well, there's also the capital G of M1 plus M2 over there's another formula too, but that's when you're dealing with large masses of objects, like polar, or not polar, but like planetary pole.
So, like something that weighs 5 tons?
Yeah. There's like capital G, which I can't remember.
Okay, so the force due to gravity between two bodies is given by capital G. It's some constant times
M1 plus M2.
M1 times M2 divided by what? Divided by R squared, where what's R? The distance between the two objects. Okay, in our problem here, we're dealing with a 5-ton satellite. Is the mass of that satellite going to change? No. We're also dealing with the Earth. Is the mass of the Earth going to change? No. So we simplify this. We use this formula just as we usually write K over X squared. where k is some constant that we'll have to figure out, and x is the distance the object is from the center of the Earth. So it's the radius in essence, correct. All right, so we're told that we have a 5-ton object sitting on Earth. So I know g is k over x squared, and typically we wouldn't call it g, we would call it F for force. So the force is 5 tons equals k divided by what's x? 4,000 is the radius of the Earth. 4,000 squared.
Would we convert 5 tons to 10,000 pounds?
No, we're okay with tons. You can convert if you want to, but typically we don't. We leave it in terms of tons. K times 4,000 squared. That's a pretty big number. That's 8, followed by 1, 2, 3, 4, 5, 6, 7 zeros. All right, so part A. We now want to take this 5-ton satellite and we want to put it 100 miles above the Earth. So we're going to have the work done is the integral of, what's our force function? K over x squared, where k is that number. 8 followed by 7 zeros divided by x squared dx. And how about my interval of integration? 0 to 100, no. And that's a common mistake people will make.
We want to go from the center.
Well, we want to go from right here. We're starting right here on the Earth. So if we're starting right here on the Earth, how far are we from the center? 4,000. And then we want to lift it. No, we only want to lift it 100 feet, not 1,000 feet. Or 100. No, it's 100 miles. I'm sorry. We're dealing with miles here. So if I want to lift it 100 miles, my top bound is going to be 4,100. And that's a common mistake people will make. People will go 0 to 100. But you're not starting at 0. You're not starting at the center of the Earth. You're starting 4,000 miles away. Equals. What's the antiderivative of 8? What's 8 followed by 7 zeros? 80 million? What's the antiderivative of 80 million over x squared? No, I don't need U substitution. I move the x up, it becomes x to the negative 2. So if I add 1 to my power, it becomes x to the negative 1, and then I have to divide by negative 1, right? So it's going to be negative 80 million, 4, 5, 6, 7, divided by x, because x to the negative 1 would be a divide by x. Plug in 4,100, plug in 4,000, and see what you get.
Why does it become negative?
Because I thought of this as being the integral of 80 million x to the negative 2. So when I take the antiderivative, I add 1 to my power, that gives me an x to the negative 1, and then I have to divide by my new power. So I divide by negative 1, makes it negative. All right, so I have minus 80 million divided by 4,100 minus negative 80 million divided by 4,000. I get...
Very big number?
Mine wasn't very big. Somebody else do it? I got 487.8. So not real big.
10 miles.
What do you mean 10 miles?
10 miles.
Oh, ton miles. Yes. Our units would be ton miles. Again, not standard units of work, but we're in a calculus class. We will accept non-standard units. In a physics class, you would probably be required to convert those to standard units. How does it change in part B if I want to lift it from 100 miles to 300 miles? What's the only thing that changes? it becomes the integral from 4,000 to 4,300 of 80 million divided by x squared dx. Is the amount of work going to triple to move it 3 times as far?
No.
No? Why not? It would be a lot easier if it did, that's true.
Wouldn't the gravity be changing as your distance gets further?
Correct. As our distance gets further from the Earth, our gravity is changing, so the amount of work required is less. So the amount of work to go from the Earth to 1,000 or from 100 miles is not going to be the same as the amount of work to go from 100 miles to 200 miles. Going from 100 miles to 200 miles, would it be more or less work?
Less.
Less. How come?
Gravity's decreasing.
Gravity's decreasing. There's less force required. Same distance, but less force. It would be less work. So it certainly will not be 3 times as much work. It'll be less than 3 times as much work, won't it? Let's see. I plug that into my calculator. Minus 80 million divided by 4,300 minus negative 80 million divided by 4,000. I get 1395.3. Which is about 2.8 times as much work. It's not 3 times as much work, it's about 2.8 times as much work. Questions on that? 10 miles, correct. Units would be 10 miles. Alright, let's look at another type of problem. Another type of problem is something like problem 15. Problem 15 says a rectangular tank with a base of 4 feet by 5 feet and a height of 4 feet is full of water. See the picture. The water weighs 62.4 pounds per cubic foot. How much work is done pumping the water over the top of the edge in order to, part A, half empty the tank, and part B, empty all the tank? What's different about this one? How's this different from the spring problem or the rocket problem? True.
You're trying to, you're moving, you have to figure out how much water is in there, right? You have to figure out, use, like, something totally different than what we.
Not really.
What's the rate?
Doesn't matter. How fast the water is pumped out doesn't change the amount of work. Just changes how good your pump is. The faster it goes, the bigger and stronger your pump is, but doesn't change the amount of work done. The weight is not changing, is it? Is the weight of water the same all the time? What is changing? The amount of the tank changes. What else changes? I think what changes is the distance you have to pump the water. Right? Because when I first throw the pump in, the pump is sitting right on top of the water. How far does it have to pump the water to get it out of the pool? Or out of the tank? Not very far. But as the water gets pumped out, the water level drops. So eventually the water level is dropped down to here maybe. And then what happens?
Instead of 4 feet, it's 2 feet.
It's got to pump the water up over the edge. So when it was right near the top, it only had to pump it just barely, right? It gets down here, it's got to pump the water 2 feet. It gets all the way down to the bottom, it's got to pump the water 4 feet. So the weight of the water is not changing. The weight of the water that it's pumping out is constant all the time. What is changing is the distance that the pump has to pump the water. So in this one we have force is constant, but we have variable distance. All right, so how does that change things? Nope, we can still do one. Here's what we're going to do. So consider, if you will, just taking a very tiny sliver of the water. So imagine if you could, imagine if it was ice maybe, and you could slice it. Hard to slice water, but imagine if it was ice, and you had one tiny little slice. How much work would it be to lift that water out of the tank? Well, it would be the weight of the water. So how much is the weight of the water? 62.4 pounds per cubic foot. Ice has a different density, that's true. Imagine if it was water, but not ice, but you could slice it and lift one slice at a time. It's easier to think of as ice, but ice might have a different weight. I'm not sure. That's possible. All right, anyway. So it's not 62 pounds. It's 62 pounds per cubic foot. So we need to know how many cubic feet in our tiny little slice of water. It's rectangular, so it's pretty easy to find. It would be the volume, wouldn't it? So in this case, the weight is going to be, well, what's the volume of our teeny tiny little slice of water? Length, which is 5. Width, which is 4. Times the height, which is? I'm going to use dy because I built horizontally, didn't I? In a sense. And I'm thinking of my water starting down and going up. So I'm thinking of my water going in a y direction. dx would work just fine. I'm going to use dy. So my weight would be 5 times 4 times 62.4 times the thickness of my little thing, which would be dy. Next question. How far does that water need to move? Well, it needs to go from here up over the top. So how high up is my water? You're close. Nope. 4 minus y. Because from the bottom of the tank to where my rectangle is, that distance would be y, wouldn't it? But if I want to go up out of the top, I want to go from here up. The total distance is 4. The distance here is y. So the distance the water needs to move would be that distance, which would be 4 minus y. So my distance is 4 minus y. All right, so my work is going to look like this for part A. Work is going to be the integral of 62.4 times 20 times 4 minus y dy. If I just change things around a little bit, 5 times 4, I called that 20. I don't know why I didn't put the 62.4 first to begin with, because that's the way I like it. So there's my weight, and there's my distance, force times distance. Now, for part A, it says we want to empty half the tank. So if I want to empty half the tank, what numbers do I use? 0 to 2. 2 to 4. 4 to 2. But we always put the smaller number on bottom. So 4 to 2, 2 to 4. We would go 2 to 4. Why 2 to 4?
Because you're emptying the top half of the tank, which is from 4 to 2.
Because I'm emptying the top half of the tank, which means the y value is starting 4 feet high. And as I empty it, if I empty half of it, it gets down to a minimum of 2 feet high. So it should be 2 to 4 if I want to empty half the tank. And again, a very common mistake there is people will put 0 to 2.
Would it still work?
You think you get the same answer?
Yeah.
Well, let's find out. All right, so this is going to be, let's do this integral. This would be 62.4 times 20 times, what's the antiderivative of 4 minus y? Close? What's the antiderivative of 4? 4y minus 1/2 y squared. And then we have to plug in 4 and we have to plug in 2. No, because this is a number that's multiplying. It's like if we had 2x, do we do the antiderivative of 2? No, we don't. So this is just a number. All right, so let's see. That's what's 62.4 times 20? That's 1248 times. I plug in 4. If I plug in 4, I get 16 minus 8 minus 1248 times, if I plug in 2, I get 8 minus 2. So that's 1248 times 8 minus 1248 times 6. I get 2496. Units? Foot-pounds this time, because our y was in feet. Now, just for curiosity, if I did the integral from 0 to 2, would I get the same answer? Well, it would be almost the same, wouldn't it? It would be 1248 times 4y minus 1/2 y squared, evaluated at 0 and 2. So it would be 1248 times whatever I get when I plug 2 in, because when I plug 0 in, I'm going to get 0. When I plug 2 in, I get 6. 1248 times 6 would be 7488.
And but that would be the answer to the next question, right? How much does it take to have all?
Nope.
Oh, that'd be zero.
Have to add them together.
So you could add them together then, right? Is that part of it?
I could. What would this integral represent?
The bottom half of the, like, because if we do the top half of the rectangle, then that would be the bottom half.
Right. This would represent the tank is half empty. So the tank only has 2 feet of water in it. So now I have to empty the bottom half of the tank. That's what this integral would represent. This would represent emptying the bottom half of the tank. Because the water started on the ground and only went up to 2 feet. So that's what that integral would represent, emptying the tank if it was half empty.
So the bottom one's so much more because the distance is so much further.
That's right. The bottom gets so much more because the distance is so much further. That's correct. Think of the water on the bottom, you've got to move it the entire 4 feet. Where the water on the top, you only had to move it just a micron to get it to dump out of the tank. Okay, so the answer to part B, we could add these two integrals together. That would be absolutely correct. But generally, we would just do the integral from 0 to 4 of 1248 times 4 minus y dy. But it should be the same answer that you get if you just simply add these two numbers together. Questions on that? All right, let's do one more of those, and then we'll call it good for the day. Oh, I don't know. Anybody have a preference? 17 or 19? 19. Oh, good. That's the harder one. All right, 19. Same idea. We have a tank full of water, except this time the tank is not an ice box. The tank looks like an ice cream cone. So an open tank has the shape of a right circular cone. See the picture? The tank is 8 feet across at the top and 6 feet wide. How much work is done in emptying the tank by pumping the water over the top edge?
It would be easier to just cut a hole in the tip and then put it that way. And then you don't put it off.
That's true. It would be much easier if we could just cut a hole in the bottom and let the water run out. But maybe this tank is underground, and we can't get there to cut it, and if we did cut it, it would just soak into the ground. Anyway, we really need to pump it out.
Unless if the company has like $1 million tank, I don't think they'd appreciate you cutting holes.
They don't want to cut, yeah, that's true. If they paid a lot of money for that tank, they probably don't want you cutting the bottom off. You weld it back on, right. All right, so same idea. We've got to figure out the distance. I think they already gave us the distance, didn't they? What's the distance? Look at the picture. How far does our little circle of water have to go this time? So our distance is going to be 6 minus y. So what's the hard part for this problem?
Formula.
Figuring out the volume of the water.
Is that like what we did in optimization? Just figuring out the volume.
It's going to be similar, yeah.
Find the volume of the real from the tip. Find the volume of all of it.
What's that?
Just thinking out loud. Find the volume of the cone with its tip taken off.
Well, but we don't want the volume of the part with the tip taken off. What we want is the volume of this little circle that's drawn here. So we don't want the volume of all of this down here. We just want the volume of that little circle.
How can you really notice it?
What's that?
How can you really notice it?
Because again, what we're thinking of is we've got this cone full of water. We could freeze the water and slice it and lift up each slice individually. So what we want to do is we want to take this circle of water here and we would want to lift just that circle. How much work is it to lift just that circle? And then we'll integrate and we'll add up the work of all the circles combined.
Just need to know the volume of the cone, right?
What's that?
You need to know the volume of the cone.
Nope. We don't need to know the formula for volume of a cone for this problem. Okay, so we have a teeny tiny little cylinder in there, don't we? It's a circle with a little bit of thickness. How do you find volume of a teeny tiny little cylinder? Or how do you find the volume of any cylinder? Nope. There's a formula for volume of a cylinder.
Yeah, it's the height of the cylinder times its base.
Times the area of the circle. Okay? So the height of a cylinder like this is pi r squared h. So our water, the weight, the force, is going to be pi r squared h times 62.4, because water is 62.4 pounds per cubic.
But it's in the cone, so how is it going to be a cylinder?
Because you're taking the individual.
Because again, we're taking just one tiny little slice along the cylinder.
Even so, though, the size would be constant.
True, but our thing is so thin that the amount of the slant really doesn't matter. And again, think about, we're eventually going to be building an infinite number of these, so the cut is going to be so tiny that there really won't be a slant. Okay, so looking at my teeny tiny little cylinder here, I think I know the h. What's h? H is delta y. That's the height of the teeny tiny little cylinder there, isn't it? What's the radius?
8 minus.
Well, the radius would be 4 feet. It's 8 all the way across. So the radius would be 4 feet if you're all the way at the top. But if you're somewhere in the middle,
Would it be
4 minus.
it wouldn't be 4 minus y.
How much that?
Not 4 minus x either. But you're getting close. All right? So x is somewhere along here, isn't it? So the radius of this, in the way they have this drawn, the radius is x, isn't it? So we know our force is going to be 62.4 times pi times x squared times delta y, or dy if you will. But that's a problem. Why is that a problem?
it's too many? We have x and dy.
If I have a dy, I can't use x's. I have to have everything in terms of y. So what I need is I need to come up with some way to relate y with x. Any thoughts on how to do that?
Is it r squared in the formula x?
R would be x, correct.
So
R would be the radius, which is the x value.
put the formula in terms of x.
Which formula?
The formula for volume of that cone.
Cylinder.
Well, right now the
cylinder.
formula is it's in x and in y.
Yeah.
I only want it to be in y because I know my distance is going to be 6 minus y. So since my distance is 6 minus y and I have a dy, I'm pretty sure I want to get rid of the x.
So find out how many y's is in x squared and then substitute.
Correct. So that's what I need to figure out. I need to figure out how many y's are in x squared. And here's how you're going to do it. Think of the picture there. You've got your cone. How far out does your cone come?
4 on each side.
4 on each side. I'm only going to deal with this side because we only need half of it, really, right? So this is the point 4, comma, what's the y value right here? How tall is my cone?
6.
That's the point 4, comma 6. So I've got some point right here where I know the x number, but what I really want is I want the y number. Not Pythagorean, but you're close. What's this right here? What kind of shape is it?
Straight line.
It's a straight line. Could I find the equation of the straight line?
Yeah.
Yes. What's the equation of the line that goes through the point 0, 0 and through the point 4, comma 6?
So 2/3.
Okay, so first off, what's the slope?
It's over there.
6 over 4, which is 3 halves. So this is the equation, y equals 3 halves x, isn't it? Since its y-intercept is the point 0, 0. So what's x? X is 2/3 y.
Square.
And then we're going to take that, and we're going to plug it in right there, and that will give us everything using the letter y, won't it? All right, so I told you this was the hard one. 17 would have been a lot easier. All right, so we're going to have, our answer will be work is 62.4 times pi times, instead of x squared, I'm going to have 2/3 y squared dy. So there's my force. And then we already said the distance was 6 minus y. And then I got to do an integral. And my integral goes from 0 to 6 because it said it wanted us to empty the whole tank. So there's my answer. Should we work it out? No? How would you work it out? Well, here's what I would do. I won't work the whole thing out. I would write 4/16 over 15 pi, the integral from 0 to 6 of 6y squared minus y cubed. So I did several steps of algebra there. Can anybody tell me what I did?
You multiply 62.4 times 2/3
Squared.
and then squared it.
That's right. So I took 62.4 and I multiplied it by 4/9. And that gave me 4/16 over 15.
And then you factored it out.
And then I took the y squared and I distributed it through. So now we would find the antiderivatives. Finding the antiderivatives would be very easy. Add 1 to your power, divide by your new powers. Plug your numbers in, see what you get for an answer.
On the test, is leaving it as work equals integral from 0 to 6 of like a cone problem perfectly okay?
On the test,
If it's a cone, like if it's one of the other ones we did, those ones are fairly.
the spring ones are very easy. The gravity ones are very easy. If it were one like this, I would be okay if you typed it into your calculator and gave me the answer that way. That would be fine. I mean, the reality is this still isn't really very hard, is it?
No,
Once you get to there, it's really a pretty easy integral. The hard part was getting to there. That was the really hard part. I would not envision a cone problem being on the final. But I haven't written the final yet, so I can't say for sure.
But there's going to be optimization there anyway.
Yes, there will be optimization problems. There will be force problems. Enough cones with optimization?